Hello. My talk today is on roadway tolling. I'm going to be sharing some research results that I've done on this topic with my students, tying in some themes of artificial intelligence and social equity. So to give credit where credit is due, a lot of the work that I'm going to present was done by these students in their theses. Venkatesh Pandey, who is currently an assistant professor at North Carolina A&T, and John Helsel, who is currently lead data scientist at WSP USA. Venkatesh's work was related to artificial intelligence, and I'll present that in a little bit. John's research was related to equity, but both of their work was oriented around the theme of roadway pricing. So both of these ideas have shown up time and time again, and especially in recent years. There have been a lot of people asking about what artificial intelligence has to say for transportation, whether this is new technologies, whether this is new control schemes, whether this is new ways of generating or analyzing data. There's been a lot of attention on AI in transportation, and there also has been increasing interest in how we design infrastructure systems that are equitable. Now, in one sense, this is not a new idea. I mean, in fact, dating back several decades, there's been an executive order in place stating that federally funded projects should not have, quote, disproportionate impacts on disadvantaged populations. But what exactly does that mean? There still are a lot of questions being asked about what does it mean for a particular project or a policy to be equitable or not. And so to crystallize both of these issues, I'm going to talk about them as they relate to roadway tolling. In particular, dynamic toll roads. This is a screenshot of what a dynamic toll road on Interstate 405. And talk about how artificial intelligence and equity manifest in this particular transportation system. So just as an outline of the talk, I will start by giving a brief overview of artificial intelligence, a brief overview of approaches to equity, emphasis on brief. You could have entire courses on each one of these topics. Then talk about some issues in toll roads in general, and then try to bring all these issues together. What does artificial intelligence have to say about how dynamic tolls should be set? What can we say about the equity issues that arise with tolls? Is it always the case that certain people are going to be worse off as a result and others are going to be better, or are there ways to address some of these particular issues? So I'll start with artificial intelligence. And so this is a term that's used a lot. And so the obvious question is, well, what is artificial intelligence? What exactly does that mean? And the natural question from that is, well, what is intelligence? Set aside artificial for a moment. Just what is intelligence? And this is partly a philosophical question, and people have answered this question in a number of different ways. Are we talking about problem solving? Are we talking about planning? Being able to react to circumstances, and so on and so forth. And so there's a lot of different conceptions of intelligence. And then what makes artificial intelligence artificial? And is there a difference between artificial intelligence and other kinds? Interestingly, there's been a lot of goalpost moving, honestly, in this, in that, decades ago, people said that, computers it's going to be, a long, long time, if ever, before a computer can beat a human being at chess. That is just, too hard of a thing to do. Well, that came and passed. Computers are much, much stronger than any human player has been. And now people are saying, well, that's not really artificial intelligence. That's just computers, just brute force, crunching a whole bunch of numbers. That's not really intelligence. Now, a game like Go, that's a game that requires real intelligence to play. Well, okay, people said that until AlphaGo came about and is stronger at Go than human players. And now people are starting to move the goalposts yet again. Well, that's not really, artificial intelligence, or that's not really intelligence. It's just brute force. So there's a philosophical debate here. And researchers in AI have conceptualized 4 different views on what artificial intelligence might be. Is artificial intelligence mimicking the ways that humans think, being able to understand the brain well enough to simulate that? Does it involve acting like a human? There is a famous thought experiment called the Turing test, which says that intelligence is when a human being couldn't tell if they are chatting with another human being or with a computer. Is this what it means for artificial intelligence to exist? Does it involve thinking rationally, as in formal logic? Can we derive sound conclusions from given premises? Or is it the question of acting rationally? Artificial intelligence is about achieving a particular goal, and the means by which we do that is maybe less important. So there's a lot of discussion about these. As an engineer, the main conception that we're interested in is this fourth one, about acting rationally. As a transportation engineer, my main concern is how can I design, manage, operate systems better than I could have before? And this acting rationally conception of artificial intelligence is the one that fits in the best with that. And just to kind of illustrate the difference between these, right, the field of aerospace and artificial flight really took off about 110 years ago or so when we stopped trying to imitate birds, but rather designed airplanes that operate under different principles, right? The goal of aviation is not to design these aircraft that look so much like birds that they will fool other birds. No, the goal is just, can we get people from one place to another safely and efficiently? And so a couple of lessons that show up in applying artificial intelligence to transportation systems. First, we need to be aware of unintended consequences, right? If you tell a computer to optimize something, it will do so, regardless of whether that's what you actually meant for it to do or not. And so, for instance, you say, how should green time be allocated at a traffic signal? Well, maybe the first thing you want to do is, let's just maximize throughput. Well, okay, so then one way to do that may be to give all of the green time to the major approach, none to the minor approach, and then, look, we're moving as many people as possible, even though this is grossly unfair to people who are on the minor approach. And so, okay, well, maybe not that. Maybe we want to minimize the maximum delay of anyone in the system. Well, if the boundary's not drawn right, then you may end up with systems that end up just prohibiting anybody from entering the downtown area, and voila, there's no delay. But there's no people there, and the system is still not operating as we think. But so you have to be very careful about what objective you provide in this. Oftentimes you'll find that there are things that have been missed. Related to this, domain expertise is important. It's important to know how these systems actually operate to try to avoid these kinds of unintended consequences. Or if a system is providing recommendations that don't make sense, knowing how to fix it. Especially in problems where both the objective is a little bit unclear and the system dynamics are a little bit unclear, as in transportation, it's very important to have domain expertise. Artificial intelligence needs to have a lot of training data. People have asked me, can we eliminate our entire planning process and just use AI to say what our systems are going to look like or what our cities are going to look like in 30 years so we can plan for that? The short answer is no. We would need an enormous amount of data to make predictions. We do not have that sort of data in order to predict with exact certainty what's going to happen in the future. The quality of the training data we give it is also important. There is been some evidence in facial recognition, for instance, that many facial recognition systems do not work as well for people with darker skin, and they don't work as well for women than as for men. And so whether this is due to, whether the training for these was trained on biased data where there were not enough women or people with dark skin in the samples, or whether there are inherent reasons why it's harder to do facial recognition with darker skin tones, for instance, in some ways that's beside the point. The point is, if you're looking to artificial intelligence as a way to avoid bias in your systems, you have to be really, really careful. If you train a system on biased data, you will get biased results. And this is a point which is quite important. And so this is a segue into the topics of equity and justice, right? Just as I asked earlier, what is artificial intelligence? I could just as well ask, what is fair? And if you ask different people, you would get all kinds of different answers, right? There are famous images like this one going around. I mean, what do we mean by equity? Are we talking about equal treatment, right? And kind of giving all three of these people a box of the same height to stand on? Do we talk about equal impact or equal results, where here the person who's shorter is given more boxes so that they can see over the fence? There are different conceptions of what we mean by equity. And one of the things that John taught me, and this was the student who had worked on this topic, was that us as engineers often lack the vocabulary even to talk about these. This is largely the domain of philosophers and people in the liberal arts, and engineers, unfortunately, don't get enough training in these sorts of topics. And so utilitarianism is one particular moral philosophy, and if I were to describe it in a single sentence, the idea is that we should find a way to, when comparing different alternatives or different policies, find a way to put a number on it and choose whichever one is going to maximize or minimize that. And this way of thinking is almost automatic to engineers. It's the way that we are trained to model situations. I can write down some formulas, I can do some computations, I can come up with a number, and then I can use this to decide among alternatives. But this becomes a little bit tricky. So in my field, there's a classic problem called the network design problem, where we are given a transportation system, and we're given a particular budget, and the question is, how should I use this budget to improve the network? What links should I upgrade in a way to make the network operate better? And classically, the objective is to minimize total travel time or total congestion. And so how might we incorporate equity into this? And a utilitarian way to do this is, well, let me come up with a number that captures equity, and then let me try to maximize this. And so there's a nice paper written by Jen Duthie and Travis Waller where they looked at the network design problem and they proposed 8 possible ways that we could measure equity. And these vary based on, are we looking at the differences between groups or the absolute benefits given to different groups and so on. They came up with 8 different ways that could conceivably represent the idea of equity, and they solved the network design problem under each of these. And interestingly, the recommendations coming out of it varied dramatically depending on what the objective was. And in fact, in some cases, there were some perverse results that were seen. The best way to achieve equity was to do nothing or to take the group which is better off and harm them. And again, this is the kind of thing where we look back and say, this is not what we want our models to do. Right? The goal is to provide benefits to groups that are less well off, not to harm groups that are better off. So utilitarianism is not the only ethical philosophy out there. For instance, Immanuel Kant formulated something known as the categorical imperative, which is focused more on kind of the motivations behind actions as opposed to the results of them, as in utilitarianism. And whether an action is acceptable or not, well, actions are acceptable if you would kind of accept this as a universal law that you should always operate in this way. It's based more on fundamental principles about treating people with respect than it is focused on the outcome. John Rawls was a 20th century philosopher who formulated something known as the veil of ignorance and said that the ways that we should be thinking about our societies, we should try to remove ourselves from that picture to the extent possible. Imagine you did not know who you were going to be in society. You didn't know whether you would be born to a wealthy family or to a poor family, whether you would be able-bodied or not, what race you would be, what gender you would be, and so on. And if you didn't know who you were going to be, what kind of society would you want to live in? And the goal here is to try to separate out the effects of a policy on me from a more universal notion of what justice might mean. So how do these issues look specifically in transportation? And so roadway tolling is an area within transportation that is, we are seeing more and more of this, and an area where both of these topics play huge roles. So tolls have been around for a long time. In the lower right here, this is a picture of Munich from centuries ago. The city of Munich in Germany was originally founded as a bridge over the Isar River, and it was a toll bridge. And salt traders would have to pay a toll to cross the bridge here, and today the city of Munich has grown up around this, what used to be a small community around this toll bridge. And tolls now, there are advanced technologies that can be used to collect these automatically. Tolls can vary by time of day, by location, and so forth. And so what's the reason for doing this? Why are there roadway tolls? Well, the obvious answer is generating revenue, but that's not the only reason why roadway tolls might be implemented. This is another famous picture that transportation engineers like to show to talk about the efficiency of different modes. And so the three panels here show how much roadway space it takes to move a given number of people. We have a number of people who can fit into a bus at capacity. And here's how much space they would occupy if they were all riding bikes. And then on the right, here's how much space they would occupy if they are all driving cars, right? Clearly, a bus is a more efficient mode of transportation than the car if we're looking at the amount of roadway space taken up per person moved. But the reason why we don't see everybody riding buses is that this mode is often less convenient. Driving a personal vehicle is often more convenient or more reliable. And so this is a question that transportation planners have grappled with for decades. How can we kind of push people from less efficient modes to more efficient modes, or how can we incentivize them to do this? And one economic answer to this question is that tolls can serve as an incentive. It can serve as a way to try to push people towards more efficient modes of transportation. But then the obvious question then, well, what is the right price for the toll? What is the amount of toll we should charge to do that? And secondly, recognizing that people don't like paying tolls, and in particular, for people with lower incomes, paying tolls can impose significant impositions on one's budget. And is there anything that can be done about this? We'll answer these questions in turn. And first, we'll see what AI has to say about optimal tolling. So there's been a long research literature on how tolls should be set, and originally these were based on very idealized sorts of facilities. Assume there's just a single link, or assume that you have just two parallel roads, a free road and a toll road, whereas modern-day toll facilities are quite complex. This is an image of the LBJ express lanes in Texas, and we can see there are multiple toll facilities that intersect, there are multiple entrances and exits, and so on. But we can model such a system if we make some assumptions on it. The results that I'm going to show, we are modeling vehicle dynamics using something called the cell transmission model, which can be thought of as a fluid model for traffic flow. We can make some assumptions on how drivers behave. We'll assume that drivers are trying to minimize some combination of travel time and the amount of toll they pay. We can make some assumptions about the rate at which travelers appear on this network. And perhaps we know the average demand, but the number of people that arrive from one interval to the next is not known. We have sensors in the network which give us some information about where vehicles are and the congestion patterns, but not complete information. We're not omniscient. The toll may be updated periodically based on the information we see from the detectors, and we'll look at two different objectives that the manager of such a system might have. Perhaps they want to maximize the revenue generated, or perhaps they want to minimize the average travel time by the people using this network. And so all of these assumptions can be encoded using a mathematical structure known as a partially observable Markov decision process. And the idea behind this POM-DP is to come up with a policy which says at any given point in time, given the information that I currently have, what are the sensors saying, what's the current value of the tolls, well, what toll should I set for the next time period? And a policy is, and we thought of as like this giant lookup table that says, for any of these situations I might end up in, what should I do next? Now, computing these policies can be very difficult. There's an enormous number of possible states. There's this combinatorial explosion. It is completely intractable to try to come up with an optimal policy that says here's the exact toll that I should set under every possible scenario that might arise. And so there are other ways to try to approximate this. And so neural networks have become a popular tool for trying to kind of approximate these complex functions that would try to say what I should do given the sensor input that I have. What is the mapping between sensor observations and the toll that I should charge in the next time interval? And deep reinforcement learning is a name given to a family of techniques for trying to train neural networks in this way and to find optimal policies in this way. And there's a number of different algorithms, but the key feature of all of them is that we need to balance what's called exploration with exploitation. Exploration involves trying new strategies, things that I have not done before, to see if these new policies work better than the older ones that I have. Exploitation is the idea that I should be doing things that I have a reasonable chance that I think have a reasonable chance of working well. I should not be wasting my time just exploring all over this huge space of possible policies, but rather my search should be directed in some way along the lines of policies that I think are going to be effective. And so these two ideas have to be traded off against each other. So I'm going to show you some results. And first we want to call back this lesson number 1 I gave for artificial intelligence about being careful about unintended consequences. So when Venkatesh and I set out to try to maximize revenue, and we gave it to the system, we trained this neural network, and we tried to identify toll policies that would maximize revenue, we observed something a bit perverse. We saw an intentional traffic jam where the way that revenue was maximized was essentially by creating an intentional traffic jam on the free lanes. And by creating a huge traffic jam on the free lanes, then you could jack up the price on the toll roads, and travelers would be willing to pay it because there was such bad traffic on the free roads. This is an intentional traffic jam designed to push people towards the toll road later on. And this is what's called a jam and harvest type of outcome, which is certainly not desirable. And so to address this, we looked at something called reward shaping, where we modify the objective that's given to try to incorporate some of these other characteristics. And so this plot shows kind of a space of a number of policies which were randomly generated. In the upper right, these are policies which generate a lot of revenue but have a high congestion as measured by total system travel time, or TSTT. On the bottom left, these are policies which have low congestion but also low revenue. And so we can see there's this whole space of policies in between that may be able to still generate quite a bit of revenue, but for significantly less congestion. And so we came up with several statistics we called jam and harvest statistics as penalties to add to the objective whenever we saw this type of behavior happening. And so after we did this, we saw results that actually made quite a bit more sense and saw quite a bit more improvement. Training is required, and so these plots show what happens over this process of exploration and exploitation as we try to come up with better and better policies. We see over time the revenue increases or the total travel time decreases as we find better policies. But there is a training process which is required here. And so the different lines on this plot represent different algorithms that we tried, and the one that seemed to work really quite well is soft actor critic, or SAC. This really seemed to learn much faster than the other deep reinforcement learning methods which we tried. As benchmarks, we compared this with a PID controller, which is another standard option that's used in the field for setting dynamic tolls. And what's shown here is the performance of the deep reinforcement learning method compared to that of the PID controller for 4 different toll systems under the 2 objectives. And in all cases, we saw statistically significant improvements over the PID controller by using deep reinforcement learning. And so this really is quite a nice tool for trying to find better toll policies, but it took some work. We had to deal with this jam and harvest issue. We had to apply our domain expertise in order to make this work, and that's an important lesson from this. And the final section of this talk is going to look at equity in tolling. And so to look at this, let's actually take a step back towards a more simpler pricing problem. Rather than dealing with a complex network with many entrances and exits, we'll move to one of the earliest and perhaps most celebrated models in transportation science, Vickrey's single bottleneck model, where there is a single origin and destination, and there are a number of travelers that are trying to travel from this origin to a destination on a single link with a bottleneck at the downstream end. And the question here, or the choice that people have to make, is one of departure time. When do they choose to leave? If travelers are leaving at a higher rate than the capacity of the bottleneck, then a queue is going to form, and travelers are going to have to experience some delay. And what travelers are trying to do is time their departure, recognizing both that they want to minimize the amount of delay they experience, but also that they want to arrive as close as possible to a preferred arrival time, denoted by T star here. And so the cost experienced by each traveler is a combination of their value of travel time multiplied by their queuing delay, and this extra factor here, which represents a penalty for either arriving early or for arriving late. Generally, the penalty for arriving early is smaller than the penalty value for arriving late, and we want to know what times people are going to choose to depart given this behavior assumption. And so if all of the travelers are identical, the equilibrium solution is one where the departure profile has this sort of triangular shape, where what happens is initially people will be departing at a rate higher than the capacity, and so the queue is going to grow linearly like this. There'll be this constant arrival rate of beta over alpha minus beta. A queue will grow linearly like this, and it will reach its peak length for travelers which are going to arrive exactly on time. Then the departure rate is going to drop to another constant. It's going to drop to gamma over alpha plus gamma, which is less than the capacity, and the queue is going to dissipate until the end of the peak. And so what we see here is that the drivers who are experiencing the longest delays are the ones who are arriving as close as possible to their preferred arrival times. The drivers who are leaving around the shoulders of the peak period, they experience little delay, but they arrive further from their desired arrival time. And these factors are balanced in such a way that all of the travelers have equal costs. And so this is how the queue will look under this classic model. Now, this is not the socially optimal solution, right? Because the demand is going to be, because of what the demand is, it's impossible for everybody to arrive exactly at their preferred time. Someone has to arrive early and someone has to arrive late. And in this equilibrium, the way that that's decided is the people who get to arrive on time have to pay for this by spending a larger amount of time in queue. But this doesn't have to happen. If we could kind of force travelers to depart at a uniform rate, put them in the same order that they were in this equilibrium solution, but force them to leave at exactly the capacity rate, there would be no queue formed at all. And the penalties due to early and late arrival are not going to change. Travelers are still arriving at the bottleneck at the same time as they did before, or arriving at the destination at the same time as before, rather, but they didn't have to spend any time in queue to do this. And so the total cost from doing this is quite a bit less. This congestion did not have to arise. The reason why this doesn't happen in the equilibrium is because of envy. I mean, the people who are arriving at the shoulders of the peak period here, they say, well, if there's no queue at all, why don't I leave closer to my preferred time? And if they were to do this, this would create a queue, and it would no longer be a stable situation, right? So even though this solution would result in lower total costs for everybody, it would require people to not be greedy, so to speak, but to somehow be okay with the fact that some people are getting to arrive at the destination closer to the desired time than they are. And so the classic Econ 101 answer to this question is to charge a dynamic toll. And in fact, if I take this queue length from the equilibrium profile and I convert that to a toll and charge that, well, now I can achieve the same situation as I would have in this system optimum, where there's no more queue. Rather than the people who get to arrive on time, rather than having to pay for that in terms of travel time, they're paying for it in terms of money. Right? And so this is what removes the envy aspect of it. The travelers who travel around the peak, or the shoulders of the peak, they don't have to pay any toll, but they arrive further away from their preferred arrival time. The people that get to arrive at the preferred arrival time are the ones who pay a toll. And so there is an equilibrium in this sense. So what's the difference between trying to determine who arrives at the center of the peak? Is it based on time or is it money? Well, the main difference is that the money collected via tolls does not disappear. It can be recycled. It can be returned to people either through funding infrastructure projects that would have to be paid for otherwise through taxes. These could be refunded to people directly. The point is that money doesn't disappear. It can be recycled within the society that we live in, whereas the time that's spent in congestion is pure loss. The time lost to people sitting in traffic cannot be repurposed in any other way. It's purely a loss. And so this is the classical justification for charging a toll in order to encourage people to spread out their departure times a little bit. It reduces total costs, and the money that's obtained by tolls can be repurposed in other ways. So the trouble with this is that if the travelers are not all alike, we might see that this toll policy would have different impacts on those different groups. So now imagine that there are two classes of travelers. They are identical in terms of their desired arrival time, but they have different values of alpha, beta, and gamma. That is, their value of travel time and the penalties that they ascribe to arriving early or ascribing late. And so just some examples of what this might mean in real-world terms. So travelers with a higher income may be represented with higher values of alpha. If you have more money, then you have more money to spend in order to reduce your travel time. Right? What about beta and gamma? Well, if you have a flexible schedule, then your values of beta and gamma would be smaller. The kind of cost to you for arriving early or arriving late would be smaller. And so travelers that are flexible in kind of this absolute sense would have low values of beta and gamma. Now, what I mean by absolute is that rather than just looking at the raw values of these, what really matters for the choice that people make are the ratios between these. Does somebody have a low value of beta because their schedule is flexible, or do they have a low value of beta just because they don't have a lot of money in the first place, and so the value that the amount of the willingness to spend to try to arrive earlier or later is not as high. And so where we run into problems is that often people who may have less relative flexibility may be absolutely more flexible and vice versa. And why is this? Well, oftentimes jobs which are higher paying may offer more flexibility in work hours. And so what does that mean if we put all of these things together on this slide? So if you have more flexibility in your work hours, this might suggest that your values of beta and gamma might be smaller, but the fact that you have more income in the first place might mean that those values are larger. And so in such cases, we might see that the group which has relatively more flexibility has less absolute flexibility and vice versa. And so just to make this concrete, I'll put some numbers on this here and showing the different values of alpha, beta, and gamma and these ratios here. So class 1 has higher values of alpha, beta, and gamma. And the intention here is to represent a group that just has more disposable income, and so they're more willing to spend money to avoid travel time, to avoid arriving early, to avoid arriving late. They just have more disposable income in general than class 2. However, if we look at the ratios between gamma and alpha here, we see that for class 1, the penalty for them arriving late is 50% worse than their value of travel time, whereas for class 2, their penalty for arriving late is double that of their value of travel time. And so this class is one which actually has less relative flexibility, even though their values, the absolute values of these parameters are smaller. And so what happens? Well, if we try to find the equilibrium when no tolls are applied, what we see is that the group which is relatively flexible travels at the shoulder of the peak, and the less relatively flexible group travels at the center. So in this case, the higher income flexible group, they're the ones that travel around the beginning and end of the peak period. The people traveling in the middle are group 2. These are the travelers who have kind of less flexibility in their travel plans. But if we apply the same toll as I showed you on the earlier slide, what happens is the order of these classes swap, and now actually it's class 2 which is departing at the shoulders of the peak and class 1 traveling at the middle. Now why is this? Well, when there's no toll, what dictates people's departure time is this relative willingness to pay. Group 2, it's more painful to them in a relative sense to arrive early or late than to experience delay, so they're willing to experience delay. But here, when there's a toll applied, travelers are being sorted based on their absolute willingness to pay and not their willingness to pay relative to their value of travel time. And so people look at this, and this would seem to be a case of inequity. The class which has less flexibility in their work schedules is the one which has been forced to travel earlier and later because they don't have the capability to pay the toll. And so even though the total costs of travel have gone down, we see that the savings mainly accrue to the group which has higher income, the group which is better off. And the lower income group is basically sacrificing their commutes in order to provide benefits to the group which is better off. And this would seem to be an issue. And so what we proposed was that a toll which is equitable ought to have the following properties. It ought to be order preserving in the sense that the order in which travelers depart is the same as what would happen in the no toll case. This could be justified using Rawls' principle of equal respect, that to show people equal respect, we should kind of set up our system in such a way that people are departing in the same order that they would if no toll were applied. This kind of reflects people's relative flexibility. The tolls ought to result in a system which is free of congestion. Tolls can always be recycled. Congestion is pure loss, and so we want to avoid that. And finally, we want to make the system revenue neutral in the sense that the total revenue ought to be the same as in the system optimum toll. The reason for that is that our motivation is to try to make travel during the center of the peak fair as opposed to making it free. So can we do this? So in John's thesis, he showed that this is possible if, and this is a big if we have the ability to charge different tolls to the two groups. And there are different ways to do this. I mean, rather than charging a different toll up front, perhaps this could be done by issuing a refund on tax returns or through some other sort of mechanism. But if we have the ability to charge different tolls to the different traveler groups, then we can achieve all of these desiderata. And what we see in such case is that the toll paid by each group would be exactly proportional to the total savings that are experienced. And these satisfy all of these criteria that we wanted. Now, to kind of wrap this up, some implications of what I've talked about. Congestion charging involves balancing a number of different factors. And reinforcement learning can be a good tool for trying to identify these better toll schemes, possibly with some reward shaping and being careful about what exactly we mean by better. But there are equity issues that are raised as well. Can they be addressed? Well, in our work we showed that, at least in theory, some of these issues can be addressed. But there are a number of practical questions. Is it possible to actually design subsidies like this in practice that could have the effect of charging different tolls to different traveler groups? But if so, then it may be possible to alleviate some of the inequity issues that tend to be associated with toll roads. So thank you for your attention. If you're interested in learning more about this research, please feel free to drop me an email. I would be happy to share with you the papers that are based on this work, or just to talk in more detail. Thank you.